Hi, everyone.
Hello.
All right. Warm-up. This is a real interview warm-up, by the way. Imagine you have a file on your laptop, which is like 1 GB large, and you want to copy it to a data center. The upload time from your computer to the data center is 10 minutes to copy this file. And the copy time between two machines in the data center is 5 seconds. You want every single machine in the data center, let's say there are 10,000 of them. You want every single machine to contain this file. If you know how to do it, if you know this question, if you heard it before, let's just let the others talk, because I think it's really fun to walk through this. So again, your computer, 1 gigabyte file, data center, 10,000 machines, your computer to there, 10 minutes, upload time, within the data center network, 10 seconds. The obvious first question is, how long do you think it would take for every single machine in the data center to contain this file?
May I suggest a formula to calculate the time?
Yes, please.
Okay, I think first we need to upload the file to a single machine in the data center. Then if we follow the algorithm of copying a file, maybe, well, it's not quite obvious, but I would suggest that one machine copies to other machines, or to all the machines it is connected to.
Mm-hmm.
And then those machines copy the file to other machines they are connected to, where the file is not yet. And so we have maybe some number which describes how many connections there are for a single machine. So to how many machines it is connected. And we derive a formula. I'm not sure how it would look like exactly, but let's imagine that one machine is connected to two other machines. But no.
Is everybody following for now? So what Sergey's suggesting is we spend 10 minutes, upload the file to one machine in the data center. And then there is this wave propagation. This machine copies to another few machines. These other machines copy the file further and further until all the machines are reached. And yeah, if you assume that the machine can copy a file to two other machines, the total number of iterations would be log 2 of the number of machines. You reach one machine, then 2, then 4, etc. Speaking in computer science terms, it doesn't really matter what the log base is. It's logarithmic complexity with respect to the number of machines to reach, because you need one extra step to grow the number of machines you've reached by a factor of k. In this particular case, that's quite a slow solution, to be honest. I mean, you can do better. We can do better. Anyone who does not know how to do it right has an idea?
I can try if you want. Okay. Well, we could do something like upload to everyone, like torrent work, basically. So yeah. So once you finished uploading, basically everyone already has it. So it's 10 minutes plus maybe a couple of seconds for the rest of the parts to interchange on the server side.
This is the correct answer. It's 10 minutes plus a few seconds, and the correct answer is the Torrent Protocol. So the remaining of this conversation on this question would be about designing the Torrent Protocol. Let's not delve too much into that, but I guess 10 minutes will be fine. Does anyone know how the Torrent Protocol works?
Probably I can give it a try. So there is a high-level DHT, centralized DHT, distributed hash table, so which contains the seed hosts. So initially, whenever there is a file, we look up for the seed host. That file is divided into multiple packets of the files. So maybe if I'm not wrong, 150 KB or something is the each packet size, and post that. So for each packet, we would be mapping like these are all the seed nodes, and from these seed nodes, we would be pulling on. So the problem in here that I see is we need to maintain a centralized DHT, which is the only biggest concern for me, at least, as in like per file we need to maintain, per block we need to maintain a DHT, as in like mapping between the file to the host. So once if we have the host, I think it would be an easy problem because we can just
yes,
fix them.
So the most important. You need the decentralized
yes.
Hash table. But in the case of a data center, if it's your own data center, it does not have to be decentralized.
Yeah.
But still, if you don't have it, how do you do it? So let's unpack this for everybody. The idea to break the file into smaller chunks and copy them independently is the main idea. I think you said 150 KB. On the data center scale, they're usually larger. I believe the size would be in the order of 64 megs. So you have your file on your local machine, and the protocol would first break this file into these small chunks, many of them, compute the hash of each of those, and then the task becomes make sure each file contains the body that maps to each hash. But then each machine in the data center can seed its own chunks to its neighbors who know they need this hash but don't have the data. Everybody follows, right? So now if it's centralized, which is a data center case, more or less, it's imagine you have a service that controls this hash map. It maps each chunk ID to the list of machines that do have the data for this chunk. That's a simple-ish problem. In the decentralized case, which is a torrent case itself, I don't think we should go too far there. But the idea is that you have to exchange data with your peers and neighbors to let them know that, hey, I have these chunks, and those machines have those machines have these chunks. So if you need a chunk and you don't have any data about this chunk, you ask your neighbors, but oftentimes your neighbors or you yourself would know where to look for it. Shall we call it done for the warm-up and do the real thing?
Yes.
All right. Real thing is actually a continuation of this. I would like to design a distributed object store. So distributed hash map, but the keys are huge. The values are huge. So similar to copying a single file to the data center, I want a huge hash map where the keys are, let's say, share 256, and the values are in the orders of tens of megabytes. The main requirement for my system is that it can scale horizontally. So I can start with 1, 2, 3, or whatnot machines, but then if this grows, if this scales, I can just quote unquote add machines and make sure that my database, my object store can contain more data. And of course, for bonus points, the way these systems are usually designed is you have this idea called replication factor. If you have 10,000 machines, some of them will die. So you would say something like, you know what? I would like each data blob, each file, if you want, to be stored on 3, 5, 11 machines at least, so that if some machine dies, whichever file is now under its replication factor is copied over somewhere else to maintain this factor. So we're designing a distributed hash map, which can also be thought of as a distributed file system. I know there are plenty of this. You would not have to do it on your own in the real life, but it still is a good interview question and it's a good practice exercise. Who wants to go first? Okay, let's take it from the other end. Are the requirements clear?
Yes. Do we need to support any of the replication strategies as well, as in inter data center? So there can be a rack failure, there can be a DC failure, or there can be a switch failure. Do we need to support any of these things, or just can we just go with the raw replication on this data center or replication on the inter data center?
Well, yeah, it's a good question. Let's focus on a single data center first.
Okay.
Intergalactic file system is a different conversation altogether. I'm not kidding. There's a thing called intergalactic file system.
I heard of this IPF. Let's not do it. Yeah, it's cool.
I don't
And
think.
what should be the rough QPS? Okay, that's it. Should be horizontally scalable is a requirement, right?
Well, I have one question. The requirement question. Do we want this distributed hash table to be masterless, or like with some main machine which coordinates all the other machines?
Excellent question. Unless you know exactly what you are doing, it is always easier to design these things first, assuming you have some central authority. I mean, I'll give you a small spoiler. This problem has a canonical solution, and we will arrive at that. I just don't want to spoil it for you right now. I don't want to tell you how it is usually done, but I want to speak I would like all of us to grasp the idea of why is this solution that is industry standard the right one. And as always, unless you really have to build something decentralized, and if you don't have a good idea of how exactly would it work, start centralized first. It just helps shape your mind.
So I have one requirement out, like what is the read-write ratio for those key values?
I think it's the most important question, actually. And what many people don't get or miss right away is that it is really easy to design, well, really easy-ish to design such a system with an infinite read-to-write ratio. As in, write once, read forever, never change.
Okay.
So let's consider this case first. Imagine this is like an avatar store or a photo store for your social network. And you always, there's no such thing as avatar for me. The file name is like the hash of the file name, or maybe my avatar underscore its timestamp. So you never have to override this file. It's a read-only thingy. You can potentially remove it, but you can always handle it later on the security mapping level, and then do the garbage collection afterwards in an offline mode. So let's first solve the problem of single write, infinite number of reads. Victor, you're surprisingly quiet. I guess you know this problem, right?
No, I don't. Not canonical solution. Like I have some ideas, but yeah, how to do it.
What are your ideas? It's even better that you don't know the solution. So what are your ideas, just upfront?
I mean, obviously, if we want files to be available on multiple machines, we need someone to know where those files are on those machines. So users won't be connecting directly to the machines. We'll need some gateway, proxy, something that will simply keep a registry of keys and machines that has those files. And like this, I mean, this is how we make it available. But I mean, to start this, we need some database, probably not relational one, and yeah.
So you would have like three kinds of application servers. Sorry, two kinds of application servers and the database. You have the actual storage servers, storage and serving layers. You have the application server that proxies the requests, asking the users where should they go. And you have the database that kind of keeps the mapping between the IDs and locations.
No, I think like in this case, like database might be even not necessary. Like if you, well, I mean, the part that store everything, the storage part, right? It will contain your key values, and your gateway will just have the keys. And on which machines it's located.
Well, you need to know which machine to go to.
Yes, and like keys and where those files on which machines those files are. Well, not files, but like the real.
So when you are the client and you need to get the file with a given hash, the value for a given key, where do you go?
Yes.
You're probably not going to ask all the machines.
No, not all the machines. So you go to some like gateway. You have this cache, and this cache will know that like this certain machines has the value for this cache, and you can go then to the certain machine and get your file.
Okay, so we have 4 components, and I'm not making a joke. I'm just trying to make sure we have the design in our heads. Then we're going to simplify it. So we have the database that maps keys to lists of machines where these keys are stored. We have the cache layer for this database. We have the application server that talks to the cache, updates it, and quickly tells the users where to go for those files. And we have the actual storage machines, right?
More or less, yes.
No, don't get me wrong. That is the right solution. That's how we should do it. The question is how to do it in a way that is self-contained and clean and easy to maintain. The natural continuation to this question, it kind of gets more advanced from this point on, but it also helps arrive at the right solution. What if a machine dies? You need to know exactly. So let's say, to keep it simple, let's say your replication factor is constant. Let's say it's 5 for all files, for all keys. So every single key should be stored on 5 machines. You have 10,000 machines and the machine 17 goes down. Hard disk failure, doesn't matter. On the one hand, it's easy to tell what exactly was there on machine 17. On the other hand, you have to reassign those chunks, those values, those data points to other machines. How do you think this reassignment should look like?
Consistent hashing is the direct solution for it, as in keeping all the rings, keeping all the nodes in a ring, and then maybe assigning a particular chord to each node, chord of a circle to each node, and go about copying them, so we wouldn't have n copies of all the keys.
Right. Well, much like for the warm-up problem, torrent was the correct one-word answer. Yeah. For this problem, consistent hashing is the 2 words correct answer. But trust me, it's not as easy to design it right away. And I'm pretty sure many of us have not built this before. So yeah. In how much detail do you think we should talk about consistent hashing? Shall we go like from the very bottom or take some shortcuts?
I think from the very bottom would be good. As in like why we need consistent hashing.
Maybe we have somebody who knows something, but not too much about it. So you could make a small intro and then we'll connect the dots.
Probably it's me. I know a little bit about it. Okay. If I'm not mistaken, we have a set of machines, and we can actually ask any of the machines, give me a value for this particular key. And if the machine we asked does not have this key and value, it knows to which machine to send this request to. Yeah, it's done. I don't quite remember how it's done, but basically we do not have a coordinator as a single one, but every machine knows how to route further the request from the client.
I think we're confusing 3 ideas here. So there are 3 ideas. We have touched on all 3 of those, but Vaga talked about A and B, and you talked about B and C. So first of all, the ring idea. The ring is actually the implementation. It's the low-level detail. Honestly, when I interview people and when I ask about consistent hashing, they talk about the ring first, but can't explain why is it needed. I feel these guys have read up something about it, but haven't really thought through it carefully. So ring is just a mathematical, like algorithmic trick to make it work. On the other hand, if you're building a truly distributed system, you can use this idea of ring-based mesh network. So machines self-organize in some loop so that A can ask B, so B can ask C, etc. And then they are arranged in a kind of a skip list fashion. So I can ask the next machine, but I also know who is the 10th next machine is. So I can go through the ring faster. It is not what is usually referred to as consistent hashing. It's a different idea. What consistent hashing does is it's just a mathematical function. It maps some key into a list of machines. So in this case, let's say I have 10,000 machines and you have a new key. So your key is a hash, not too long. Your value is tens of megabytes large. If, or more like when, you know exactly which machines are currently up and running, consistent hashing is just a function that takes your hash as the input, takes the list of machines available as the second input, and returns not even top 3 or top 5. It actually returns the sequence, the ranked order of which machines to go to, and you just take top 3 or top 5. The way it does it, the best way to explain it is, imagine your machines are numbered. Imagine you're not going to add random machines. Imagine you only have machines indexed from, let's say, 1 to 65,536. In this case, you can say that consistent hashing is what maps a random key into a permutation of these 2 power 16 numbers. And then you just go left to right in this permutation and you pick the first 3 or 5 machines that are up. Makes sense, right? The trick is the permutation idea, because if you do it this way, if one machine dies, you are guaranteed that the distribution of where the files from this machine would have to go to is even, it's uniform. If your machine 17 out of 10,000 had 9,999 files, ideally, it will be reassigned so that every other machine gets 1 file from it. It would never be this even, but it should be something like that. And if what you actually do is you map the key to the permutation, to the order at least of all the machines, it's clear to see that once you remove machine 17, some files for which machine 17 was, well, in any of the first 5, where machine 17 is off this list, you have to go to the next one on the list, and this next one is evenly distributed. No matter whether machine 17 was the first one or the 5th one, since all the permutations are random, the next machine to enter this top 5 list will be drawn from a uniform distribution. Makes sense, right?
Mm-hmm.
Now, there are 2 issues with this solution. One is that it is really slow to go through to compute the whole permutation and then to go left to right, because if of all the 65K machines you have like 20 up and running, it's going to be a huge waste of resources to just go through this list left to right. More importantly, it assumes the machines can be assigned numbers from a certain predefined space. What you want to happen ideally is that you can always add machines with arbitrary numbers or indexes or even keys. So you can use like IP addresses in a data center or any unique machine name. So you can kill machine 17, and it's not machine 17 of this ranked list. It's machine ABC 28, 27, 35, whatever. It goes down, and then you add 10 more machines, which are called XYZ whatever. You don't need to know exactly what the universe of machines you have. All you need to know is the list of machines currently active. So once the new machine enters this list, it's inserted into this sorted ranked order, just in the right place. You guys with me so far? This solution is neat because as long as you have some log file system, if you have some later elections going on, you do need to have some small distributed hash map. It is sort of the same thing we're doing, but a lot smaller. That keeps track of which machines are currently up and running. But as long as you have it per data center, and of course, each production data center has a log file system, you don't care. You just need all your machines to know what other machines are currently up and running. So this design is fundamentally stateless. As long as you have this log file system, it's passive. All it knows, all it can do is tell every other machine upon request what's the list of currently active machines, and you can subscribe to this. So you would be quickly notified if machine 17 is down. Not from machine 17, obviously, not from its neighbors, it's too hard, but from this log file system, from this data center management tool. Now, the ring is just the algorithmic idea to quickly get to the right number. And Bhagav, want to tell us more about this?
Yeah, I can give it a try. So it's inside our so for each hash we would be encoding this hash into some, maybe we can just consider it as a large number of 2 power 30 or 2 power 40, and divide each of this space into like one. Our primary thought can be maybe equally divide the chunks inside this 2 power 20 key space. 2 power 20 is 10 power that's 10 power 6, which is low, I guess. I think maybe we can consider it as 2 power. Sorry.
People usually take a larger number.
Yeah.
I mean, either you have a huge array to have an order of one indexing, or you take like 2 power 64 and you do a binary search there.
Yeah. So maybe we can go with the 2 power 64 approach, and then we have 0 to 2 power 64 keys. So for every file, we just hash it to one number inside this 2 power 64 list, and inside this 2 power 64, so maybe we'll assign equal number of chunks to each of these nodes. So but then we'll quickly run into the problem of like maybe one node has higher, one node can handle more number of keys than the other node. So something like one of the nodes we might be having like 5 TB of hard disk, and the other node might be having just 1 TB of hard disk. So we want to fit 5 times more keys in the one key, one of the nodes. So maybe we can go into the idea of like having the virtual node, and then these virtual nodes are have the constant space in this hash list.
That's a good point, but you're getting ahead of yourself. So what Bhagav is saying is that not all machines are created equal. If the limit is disk space, you may have a machine that has 10 times hard drive, in which case you probably want to make sure it gets 10 times more the load. So you can imagine this machine just ends up being in this list 10 times under different IDs. Or you can configure it so that this machine gets 10 times more, like 10 times the hits. But it's a different conversation. The trick is, so yeah, forget the ring for now. Consider the axis. This would be 0. This would be 2 power 64 minus 1. Each machine, more like each machine name or each machine key, let's say each machine to keep it simple, draws a random number, draws a pseudo-random number based on its name. And this number is thrown on this line somewhere. If you do it with just one number, it's going to work somehow, but not so well. So bear with me for a moment. Let's say you draw 1,000 numbers pseudo-randomly from this. All you know is this machine's name, but this machine's name is something this machine knows and all the other machines know, because this list of machines currently up and running is available. So in a pseudo-random fashion, based on this machine's name, you generate 1,000 random numbers, pseudo-random numbers, from the range of 0 to 2 power 64 minus 1. Now what happens is, let's say you have 3 machines to keep it simple. Imagine a machine A throws red dots on this line, machine B throws green dots, and machine C throws blue dots. Now, when you have a hash, what you do is you take this key. Well, when you have this new key to store, where the key is a hash, you hash the hash or whatnot, just map it to this to power 64 space, and look at this point. So you have this axis. You look at the point. You need to find the nearest point to the left or to the right. You just need to agree which direction. And that's the color of this dot, red, green, or blue, would be the machine you need to go to first. Then you go further, ignore all the other colors, and then you either hit green first or red, or you either hit green after red, or you hit blue after red. So if you have just one point per color, there's a good chance they would not be evenly distributed. If you have 1,000 points per color, what you have is this axis is colored into multiple segments, some red, some green, some blue. The color of a segment is just the color of the point right most to it. So like take each point and draw it further along the axis. So you would have approximately 33% distribution between the color of this thing. And it's only called a ring because there is a tiny chance you have to cross the zero. So it's not this axis, it's this axis. So when you go clockwise, there's a non-zero chance the next point will be past zero. That's it. So now if your range is small enough, if let's say it's to the power of 20 or even 30, you could store it in memory. So you would have an order of 1 lookup, and you would know which color covers this range. But if you just want to solve this problem in an interview setting, you can say, hey, I can do binary search. All I need to do, not the binary search, I can do this interval tree traversal. So finding the number that is, finding the largest number not exceeding something in a sorted data structure is a trivial task. Trivial in terms of system design. It's an algorithmic problem by itself, but it's solvable. How much of this should we decompose further?
So are we doing this routing at the application layer level, or somewhere we have some load balancer which is deciding where to go?
Excellent question. It depends on how effective do you want to be. If I'm the designer for the system, I would say that my client library would do that. Since I'm only going to access this file system, well, mostly going to access this file system, this object store from within my data center. The machine from which the request will go has the knowledge of which other machines are currently up and running.
Mm-hmm.
So I would say, hey, I have a singleton in my machine. In my client-side library, I have a singleton. Mm-hmm. It retrieves the current status of which machines are currently up and running. It builds this ring. It subscribes to all the updates, and it updates the ring accordingly.
Okay.
So whenever you're making the request for a certain file, this machine already has all this ring built in memory. So it's a very quick lookup to figure out which machine or which machines to go to.
Mm-hmm.
So in this case, as long as you have the centralized or semi-centralized, so centralized as in single machine you know will not die, or pseudo-centralized as in log file system, literally like that log file system you don't have to control, it just exists in your data center. As long as you have these, you can afford to not have any leaders, any central authority within your own file system. It's just in your client-side library. Now, of course, if clients from outside this data center would need to access these data files, these data objects, these blobs, values by keys, you would have, as Victor suggested, some middle tier gateway front-end cluster or whatnot of a number of machines, which would be responsible for exactly this. Their work would mostly have to do with data routing, not figuring out where to go.
Okay.
Because they would know immediately where to go for a given file. They will probably do more routing work, and they will probably have to potentially connect to more than one machine, so that if the connection is saturated, the client still gets the data. So if my replication factor is 5, my front-end router can not go to one machine of 5 at random. it may decide to go to 3 or 4 machines and open connections to all of those, just in case if one of these links is saturated, the client doesn't notice them. It's a standard technique too.
Yeah, correct.
Making sense so far?
I didn't follow the last part, so can't we just go round robin around, like these are the hashes of, these are the list of missions that I need to go for?
Well, round robin works, random works too, random of 5. There's this there's a special kind of failure called bad apple. So imagine one of the routers on one of the racks is slow. It's slow as in it's 2x slower. Some driver failure, some chip is misbehaving, and on a kernel level, this particular network card is 10 times slower. You want to make sure this doesn't, I mean, you want to alert your SREs and they would replace the rack or the router or whatnot. But you really don't want this to affect the customer who only needs to get that one chunk from your system. It's actually one of the interview questions I've bombed in my life. I didn't realize that bad apple problem has a simple solution. Yeah, now it all sounds simple, but the tricky part is, so when the machine dies, somebody has to orchestrate making sure the replication factor of the files that this machine contained is still respected. So how does this happen? Everybody thinking?
We need someone orchestrator who will do it.
And some of us, so we know the list of hashes. Someone just like posts the list of files that we need to like backup, right? And then each machine that can do this, it takes the file. If it took the file, it's taken off from the list of files that died, basically, right?
Okay. So first of all, it's not clear that all machines know all the files.
Every mission knows about every other mission, right? So as in, like, if one mission goes down, and every mission knows like what key space it's responsible for, and based on our replication factor, the next node is responsible for it. So that node gets active, and it's that node's responsibility to pull it from the neighbors.
So
I would assume it's somewhat kind of like this.
Yes, but it's not a complete answer. So I think Julia had a good idea. So you have the orchestrator.
We need master who will orchestrate it.
Which would do what?
So if the one of the nodes fail, it should be responsible for it. It should know that this node fail, and we don't ask it not for something until it recover. And also it should like reassign the load from that node to others.
So the reassignment part is kind of taken care of because we have consistent hashing. The part is to figure out which files have to be copied. And we don't, so it is kind of simple if every single machine knows the list of files. And it's not a bad solution, by the way. It's not a bad idea. If you don't have too many files, you can just say that each machine knows all the keys in this, well, let's call it file system. So knows all the file names, but only stores the data for what it's responsible for. Let's solve this case first. Let's say every single machine knows the names of every single file stored in this file system. Do we even need the orchestrator in this case?
So that's like masterless schema if every single machine knows, and we don't need an orchestrator.
I think Maxim was saying the same thing. Yes, I don't think we need that too. Yeah.
Can I say? I think we can. Everyone can be responsible for checking if they have the necessary files. Basically, when the schema changed and we know the new ring, we can check if for every hash we are in the 5 servers who needs to have that file, we can then ask for the rest servers who has it to give it to us. So basically we can backfill the void that is happening.
Well, yes.
Clear, no?
The
So if you know all hashes,
it's simple. The asking part is simple. The backfilling part is simple. If I'm the machine and I just know, hey, I need to have a copy of that file, I know where to go for it. I know how to ask for it. That's pretty much the same client-side API. The tricky part is to know that I am currently in possession of some new files that I don't have yet. I think what both you and Julia are suggesting is that if every single machine has the list of all the files, then on every single notification of any other machine going up or down, every single machine not only rebuilds the ring, but also goes through all the files, all the keys, all the names, and checks if this machine is currently responsible for keeping an extra copy of that file, right?
But it can be slow a little, maybe. But I don't know amount of keys and amount of storage. We didn't discuss it, I think.
Well, as always, consider the extreme case. You can have files of 1 kilobyte size, highly not recommended, but you can have a lot of small files, in which case, I mean, look, if k is the factor by which your file is greater than its hash, then it's key. Then for k equals 1, you have to scan all the files. For k equals 10, you would still have to scan through 1/10 of all the files. And keep in mind, every single machine would do it. So the amount of work you would do would be ridiculous. It's like super huge. Julia was mentioning the orchestrator. Maybe that's, in theory, it's something. It is a job you can outsource to the orchestrator. Just dedicate a machine or a few machines. They would go through all the file names. Is this what you had in mind?
Mm-hmm. So, but the weak point here becomes orchestrator itself. In such an approach. I mean, if orchestrator dies, we need to choose this orchestrator. We need to choose another orchestrator.
Well, technically, this is not a big deal because we know we have this log file system. We know we can update the ring by recomputing all this pseudo random hashes. So we can always just say that, hey, once every machine is notified about the change in the list of machines currently up and running, there's a fixed procedure that pseudo-randomly selects 1 or 3 orchestrators out of all these 10,000 machines. So once you have the log, this is extremely important in system design. Once you have the external leader-elected log file system, once you have Zookeeper or console or whatnot, anything with route-up access, you only need that to exist. Once that exists, all your leader elections becomes a non-issue. You can do it in a pseudo elections way. You outsource the elections to the already existing implementation of route-up access, and you just have a fixed procedure on how to pick the right 1 or 3 machines from this 10,000 or whatnot. The problem with this design is that the orchestrator handles extra load. So suddenly the files that have to be served from this machine are served slower because its CPU is busy doing the scan through all the files task. It's okay because we can have our client-side library to not put extra load on the orchestrator. Because our client-side library, the code that runs, the part that rebuilds the ring, the singleton within each machine, be it the gateway machine as Victor suggested, or be it the node itself. The client-side library can just be gentle to the machine that is currently the orchestrator. It could just exclude that from the random selection of files. It's slightly uneven, but it does the job. Is everybody following? So we have this replication factor respected, but for a few files which have one of their replicas on the orchestrator machine, effectively accessible replication factor is slightly smaller by this one machine, because we let that machine do the orchestration, the reshuffling, reassignment work. That's one solution, but it's honestly not the best one. We can do better.
Do we basically have a problem that we do not want to select one machine to copy all the files to copy all the values to from the machine that just died, but we want to copy?
It's important. Sorry to interrupt. There's not going to be one machine that does the copying. All it does is tell other machines that, hey, you should copy that file from there. It's not that the copying goes through this machine. Back to you.
No, I'm thinking.
So one edge case is coming to my mind is like while to writing to the leader, if that leader goes down and we are not able to fully write, and meanwhile it goes down, then how do we handle that data loss of that particular data? So
well, there's no data loss, hopefully. There's replication factor loss.
I mean, the first time we are writing to the leader, and in that case there is no replication. So at that time, if leader goes down, then
wait. You mean the leader that is responsible for uploading the files?
I mean, the first time saving that particular hash and their value.
But that's not what you need the leader for. So if the data center is in a stable condition, you know exactly which machines are up and running. Then in order to upload the file to this data center, we use the idea similar to the torrent question before. So imagine there is, as Victor suggested, there's a front-end cluster. There's inter-data center part, and there's the gateway between the outer world and the data center. All the machines in this gateway cluster know exactly, they have all these rings built. So when the end user says, hey, I have this file, I have this 1 GB file, copy it over to this file system with replication factor 5. It's the same as the torrent solution we had before, except you only copy it to 5 machines. So there's no leader needed here. In practice, you would even go as far as saying, you know what, once this file is on 3 machines at least, you can return true to the caller, assuming that even if something goes wrong, this file will be distributed further. That's not the best way to handle it, but it's possible. So the upload part does not need any leaders. Again, as long as your gateway machines are connected to your log file system, both in terms of getting the current state and getting the updates. So every single machine in the data center that's responsible for doing anything with our files has a singleton that listens to all the updates on what's up and down, and it's responsible for making sure the ring it has in memory is true, is consistent with reality. What Julia is talking about is when you need to rearrange data, reshuffle data when one machine dies. We need to figure out which other machines should get the data that is currently under-replicated from which other machines. So let's say you had a replication factor of 5, and you had 10,000 machines. One of the machines dies. This machine used to be one of 5 that stores some files. So approximately 0.05% of files will be affected. 5 over 10,000.
Correct.
The files that were affected must now have their new 5th home, because with this machine dying, they are under-replicated. They're not gone. The replication factor is just temporarily down from 5 to 4. So what the orchestrator has to do is to come up with a list of these files. It needs to come up with a list of jobs. Machine X should copy that file from machine Y. In fact, you can only tell machine X, hey, you should get that file. Machine X knows exactly where to go to. it would know the other three machines. It lives on 4, so machine X knows the other 3. No, wait, machine X knows the other 4. It's not 1 of 5. So anyways, it's the same client-side library. It's the same logic by which you can retrieve the file. The only problem we have left with is how do we make sure that every single file that is currently under-replicated is being notified about? We need some entity that tells some machine, hey, you need an extra copy of that file. Go grab it.
Do we need an extra entity? So can we? So I was thinking in this lines as in. So previously we were distributing the hash approximately around, like, let's say 1,000 machines. Now there are only 999 machines. So we recompute the hash. So, and then every node knows about the difference. So recomputing the hash wouldn't take much time as well. And every node knows about the difference in hashes, and every node knows like who is responsible for it.
Well, yes, this is a precisely correct statement, except one detail. Every node knows the difference in hashes if it applies this logic to every single file.
Yes. As in, it can, I was thinking like it can go through all the key spaces in this. If it's the range of like 1,000 to 1,200, so this node will query for 1,000 to 1,200 to that particular machine, which was holding this data, and then it can send it in a bulk for all of this these files.
I think you're onto something, but I'm not sure everybody quite followed. So what's this 1,000 to 1,200?
Yes. So what I mean is, let's say we computed the hash, we recomputed the hash of the current existing machines, and every machine knows like which range is missing. As in, the previous node was holding the let's consider it as 1024, and there are 1024 machines. So everyone used to have just one key, and now there are like 102, 1023 machines, and now one node should have one key is missing. So now during the rehash phase, so people, the nodes need to know like some of the node need to take care of this one particular data point. So
hold on, this is all true. What you're saying is that once I have to recompute the ring because some machine is down,
yes,
I can recompute the ring and make the diff between the old ring and the new ring. And I can see exactly which parts of the range I am now responsible for.
Yes.
Which will be a tiny fraction, tiny fraction. Just think about it, because it's the difference between 10K machines and 10K minus 1 machines is sorted across all 10K machines. So it's a tiny difference, but it's still, I hear you. That's the right answer. But we still don't know which files are in this space unless we have the files already sorted by that key or whatnot. You would still have to go through all the files, right, to recompute their hashes? Or no?
We don't need to, maybe. So initially our hash is directly linked to one of this 2 power 64, right? So when I have the hash of the file, so I compute it in the 2 power 64 range, and it's mapped to one number. So now we have the range of numbers, so we can directly query the files.
Okay, yeah, that's good. It's a good optimization. If you keep the file, if you not only keep all the file names and all their hashes, but also you keep their hashes mapped to the list. I mean, you have the sorted list, so you can binary search for this each tiny segment you currently own.
Yes.
Each machine would quickly know if it needs any more files. This is true. This is correct. That's a good way to do it. One last step to make. What if not all the machines know all the file names? Can you still distribute the load in more or less even way without putting extra load on all the machines? I know it's tricky, but it's a fun exercise.
You have your number of, like, if in your ring you have a 33% per each machine, right? You can have more percent for more machines that like can perform better. And when you do random distribution.
Oh yes, you get it somewhere. You're saying, hey, there's 100% load to be distributed, but I can share it across machines. But then again, it's what Julia is saying. We need the orchestrator, and the orchestrator means either elections, and it's a single machine or just 3 machines that are busier than others. Uncertain if it's a good idea. Might work, but not clear. Well, what if I tell you that if a machine is gone, there are still 4 other machines that know which files used to be on this machine?
Yeah.
So instead of looking at the diff in the direction of which new ranges do I currently own, you can look at the diff in the direction of which ranges have been given away, which ranges that I own are currently being reassigned to other machines. Am I being too fast?
I think so.
So let's say I'm the machine. I have my small fraction of keys, and I get a notification, much like everybody else gets a notification that one machine is down. For all the files I own, I know exactly if they were affected. I don't need to recompute the new assignment for every single file in my file system. I only need to recompute the new assignment for all the files I own. And then I can notify the other machines that, hey, you need to send this file there. Now with 5 as a replication factor, it would mean 4x work, in a sense that the machine that needs to get some chunk of data will be notified 4 times by 4 other machines. Hey, you need to own this. Please copy this from us. But 4 is still a really small replication, really small overhead here compared to, well, a huge number. That's the standard trick that is worth pondering on. All right.
Can I ask a little question? Do we consider this server dying like an atomic operation, because several servers can die at the same time, so it can become tricky very fast if we can't process it fast enough. There's recomputation and just sending files.
Well, the answer is twofold. Keep in mind, we're still largely relying on the fact that we do have this log file system. So it's not really about the rate at which 2 machines can die. It's about making sure we can recover at the rate that is much faster than the rate of change. So let's say every minute something happens. Every minute a machine dies or a new one is added. As long as we can, on average, redistribute the work in the next few seconds, we're good to go. So it's fine if it's a Poisson process. If we're talking statistics, if it's 1 per minute on average, there will be a minute where 3 will die in 1 second. But as long as we outsource this ordering of these 3 notifications to our log file system, we don't care. We're going to receive them in some order. We're going to process them carefully, and we're going to give orders of which files should be copied to where. That's it.
But do we actually need to process every event separately? We basically need to process them as a whole, like the last one, and just make sure that 5 machines have it. So it's not you don't even have to do it multiple times, I think.
Well, yes, again, it's important. It's a very good point. It's just in this particular problem, it would not be important in practice. But what you're saying is true. You don't necessarily need to process every single notification. You can be eventually consistent on each machine. So imagine you have a random delay of maybe up to 10 seconds before you actually get to bother with this ring computation. You don't need to act on every single notification. Machine B is down, machine C is down, machine X is up. You can say, oh, something has changed. Good to know. Even the current state. And if the delay between something changing and you requesting the current state was such that more than one event has happened, you only care about the last state. You still need to look at the diff. So if every single singleton and every single machine looks diff to diff, looks state to state. If one of the states has multiple mutations collapsed in it, it's fine. As long as it can give proper reassignment orders. You guys copy that from there. Yeah, in practice, that's what proper PubSub would do for you. You would get a notification, but by the time your callback is called, your callback would have a parameter that, hey, you have this new event, but there are 5 more. And it's on you to decide how many of them do you want to process right now. You can default to just processing the first one, or you can squash them by your own logic. In this particular case, you can squash everything but the last one, as long as you compute the diff between what you had before and what you have now. Am I making sense? The last bit of information here, I think we actually covered this pretty well. And I'm happy that for the first time we have an under 1 hour meeting. The last thing to cover here is that in addition to removing machines which die, you can also add machines. You have this scaling technique. And interestingly enough, adding machines works the same way. The machine is up and running. Your node, your singleton, your whatnot is there. It notifies everybody else via this log file system that, hey, I'm the new node. Give me fractions of your data. Instead of other machines having to catch up for what has died, the other machines can now offload their load. So, hey, I don't have to keep this file because I used to be I used to be the 5th on the list. Now I'm 6th. And the replication factor is only 5. So I can keep this away and delete it. Usually deletion won't happen right away. It's not a good idea to delete data like this. Usually deletion happens later on as a vacuum process or whatnot, some latency, but the idea is clear. You just need to make sure that the logic you use to compute this diff would be responsible for both directions. So as you were saying, Bargav, you need to compute the diff both ways and give both orders, copy to and copy from. All right.
And how do we recover from if there is a network crash or something, and we ended up in like some nodes not communicating with other nodes? So how do we recover from those kind of states? As in, like, now we have solved the base level of the problem. Now, if we venture into the real world problem of like, if there is a partition or something between these nodes, and every other node would think like, I need to be responsible for this hash, and they start replicating, and then after some time, they know like every other node is again visible.
Well, a couple answers. First of all, if it's your own data center, you don't have to deal with this degree of split brain in practice. So you don't have to plan for that. You can just assume that if the machine is up, it's accessible. And if it's not accessible, then some daemon on that machine would report it as down or partially available, so that in your log file system, in your upright nexus that is leader elected, that stores the state of machines, this machine will be declared intermittently unavailable. So in practice, I think the shortest, most important answer to this is that system design is mostly about making sure you can reason how do you build complex systems from simple components. The key takeaway, so honestly, I think when you take a system hashing, it was the biggest takeaway for this problem. The second biggest takeaway is that you can use one single leader elected data authority. You just outsource everything to that. The moment you start thinking about how do I maintain the data on which shards of which nodes are unavailable because maybe some switch is down, you're solving someone else's problem. It's not something you have to do. Your client-side code would fail. Maybe your node would just declare itself unavailable. Or maybe your node would notify some external alerting service that machine seems to be unavailable from me. And then someone else outside your service on the data center level, some other service would be alerted, some other person will be paged, and they would think that, hey, a lot of services, one of which is your file system, is telling me that that machine or that rack is unavailable. So from the system design perspective, especially from the interview perspective, I know we're kind of changing formats. We're not really talking about interviewing, but from a system design perspective, number one is consistent hashing here. Number two is rely on one single external authority that has leader elected consensus. Everything else makes the problem a lot harder, because effectively, if you want to deal with split brain, you'll be reinventing Bitcoin, which is super hard. By the way, pragmatically speaking, what we have not covered here, there are a few continuations to this problem. One is, what if files do change? We kind of assume that for a given key, the value never changes. In practice, if you go to, well, first of all, let's implement deletion. To delete the key, you need to mark it as deleted, so that your machines that keep this key no longer serve it as available. That's the tricky part, because you can mark it as deleted on 5 machines, but one of them dies in the middle, and then the new machine gets this file, and it doesn't know it's deleted. You could say, hey, you know what? I'm going to keep this list of files and their deletion mark in yet another log file system. But that's ineffective. It's going to put a lot of load on that. So you probably will need to design something like a directory on your own. So part of the CPU of each of your machines would be responsible for making sure that the deletion flag is propagated properly. And then once you have deletion, actually, updating files is kind of easy, because you just change the mapping. Your file name becomes a small hash map from hash to hash, from key to key, where your internal key is like a blob ID, like in a torrent key, and your real file key, your real key in your fused key value store is just a pointer, a symlink to what this file is supposed to be. And now you have a real distributed file system, real GFS, if you wish. Actually, I'm pretty sure HDFS works like this. Hadoop file system.
Even Cassandra has something somewhat similar to this idea.
Yeah, I could have done better. I was kind of I used the terms object storing documents, storing keys, and file names interchangeably. Originally, I framed this question as, let's design Cassandra, but then somehow it turned out easier to reason about the file system. I hope you guys don't mind. All right. Any questions that are worth covering during the recording? I'll stop it then. Thank you, guys.